Here we are again. Welcome to the physics video lecture. Psci 168, video lecture 21. So we have an exam this week on Friday. So today I'm just going to do a review that'll give you plenty of time to prepare. And it's a good time to get an overview of everything we've done. And then next lecture we'll continue on with thermal physics. So yeah, we've got the full hour or however long it takes to review for the exam. Let's go ahead and note that it's going to be on Friday, and I will mail you an exam around 11 o'clock and you'll send it back to me around 12 o'clock. Okay. So yeah, the same way as before, take pictures of your work, email it back to me. So yeah, we have that dialed in by now. And so what are we going to cover? There will be no surprises. I'm going to outline what you guys want to do or have to do. And that way we get, like I said, the overview of everything we've done so far. So, good. Let's begin with where we started. We started, well, with people running around chasing game in the desert, but we quickly went to the sundial and we went to geometry. So I'm going to begin with some geometry. You know, we did a fair amount of interesting stuff. How to measure things, and I have as an example, if the sun is casting a shadow, well, let's say if a big tree casts a shadow in the sun, and there's the tip of the shadow right there, and I'm standing here, and the end of my shadow is right there at the same end of the tree's shadow. That's the idea, right? We've got sun coming in here, and we're going to label this again. So the height of the tree is capital H. The distance from this origin is capital L. Okay, my height is lowercase h, and the distance from where I'm standing is lowercase l. Well, good. Let's use another color. We have similar triangles. What's so important about this example, similar right triangles, is that we can extend this and basically measure everything. Okay. So the basis of surveying, of measuring distances, everything, you know, properties, cities, mountains, the moon, it's all based on this. Good. So what do we have here for similar triangles? The fact that these two, the small triangle in the corner and the big one, are similar means that any ratios of lengths characterizing these triangles are the same. So in this case, we have for the small triangle h divided by L, for the big triangle capital H divided by capital L. You need to know 3 of these and you can find the 4th. Okay. So in the practical case, you want to know how tall that tree is, you know how tall you are, and you pace off these other lengths, and you solve for capital H. But you can solve for any of them. Okay. So solve for H. So that's a good example, and we learned those kinds of things, and then we said, let's extend it. We've got the meter stick. How big is our Earth? Okay. So a second important problem is the shape and size of Earth. Okay, so second problem, shape and size of Earth. So what are some of the arguments for the sphericity of Earth? arguments for the sphericity of the Earth. So you want to look those up and remember them and see what they are. All of these kind of things, you only have an hour, so you really got to knock it out. When I ask you this, some question relating to this, you basically hit the ground running. Okay. So you want to know what the arguments for the sphericity of Earth are, and I'll remind you we had things to do with the phases of the moon, the shadow that the Earth casts on the moon, so lunar and solar eclipses, that all came into play. Other things as well. Then we have the actual construction by Eratosthenes and so this sketch here is very important. What does this sketch mean? We've seen it a number of times. Maybe you haven't seen it for a couple of weeks. Well, we have a circle and we have two parallel lines. They represent the rays of light from the sun, these two parallel lines. Circle is the Earth. The radius of the Earth appears here twice. Okay. There is an arc length between these two. It's a north-south distance between these two points here. These little dots that are red. One of these is Alexandria, and one of them is Aswan. And there's an arc length S. Okay. So here's the thing, the assumption that the rays are parallel tells us that this angle here that we can measure is identical to this angle here that characterizes this circle. Okay. These two angles are identical. This one is measured. And what is this angle? Any line away from the center of Earth represents straight up and down. So that would be this ruler, straight up and down. And then the ray of the sun is coming in from a lower position than vertical. So there would be an angle there. Didn't bring a second ruler, but straight up and down, and then my arm would be the ray where the sun is. I'd be pointing at the sun with my arm, and then there's an angle being made between my arm and the ruler. So yeah, you got to practice that, wrap your mind around it. This north-south distance between Alexandria and Aswan. It's not the equator, but the way I've oriented this circle and these rays shows that the sun here is directly overhead. It illuminates the bottom of a deep well. Up here, the sun is not directly overhead, just as I showed. But yeah, there's a story behind this graph. The radius of the Earth is unknown. The angle can be measured. Okay, so look that up in your lecture notes. We did this in great detail. But like I said, there's a story behind everything here, and yet here we have a very clearly defined geometrical problem. And then we're going to use that there are 360 degrees in a circle, so we can say that that angle is to 360 degrees, okay, as that arc length is to the entire circumference of the Earth. And when you solve this simple equation for R and plug in the angle that was measured, then you actually find that the radius of the Earth is 6.37 times 10 to the 6 meters. So really, this is one of the all-time great problems in calculations. And for future reference, we could do this. We don't have to have access to Aswan and Alexandria. We could do something similar, say, between, say, the Mexican border and the Canadian border, right? And we would, instead of measuring one angle, we'd measure two angles. We'd have a difference of angles, but it would really be the same construction. So we can do this between any two north-south locations. In fact, how about if I draw this other construction? Because we do want to be independent of the idea that we have to have the sun directly overhead. This is the generalization. The generalization of that picture. So I'll just write here more generally. So once again, we've got our circle. I'm going to go ahead and draw this ray here, but now we have two locations as I've drawn them here in the northern hemisphere. We have two different locations. We have two vertical, both of these lines represent those vertical sticks, and we have three of these parallel lines coming in, okay? So I will label one of these points A and the other one B, and I'll take a theta sub A here, and theta sub B is this entire angle. Okay, theta sub B is from here on up to there. Okay. Theta sub A is just the small one. So if I have an arc length S, I'll call it S sub BA or something, or I'll just call it S. Okay. There's the radius of Earth. Yeah. You can see the same argument for this wedge holds true for this upper wedge. Let me go ahead and draw this upper wedge in black. The upper wedge I'm talking about is this one here. Okay. So for that wedge, we have the difference between these two angles, which gives us this angle here for the black wedge. Theta sub B over theta sub A divided by 360 degrees is equal to that same S up there, 2 pi r. So you see, we would be able to do this for a city somewhat above, further north, and then one further north still. So this generalizes the problem, and we could do this with a little cooperation with our friends who would agree to do the same angular measurement as we do some afternoon. Okay. So yeah, this is foundational for locating your position on Earth. Of course, this is the daytime sky. There's the whole world of the nighttime sky as well, but this was enough astronomy for our purposes. Okay. Very important. Okay, shape and size of Earth. Excellent problem. So what do we do after that? Geometry, measure the Earth. Then we started talking about forces, right? This is a class about energy. So for our third type of problem, we have to know what force is. So if I ask you about force, well, then you say it's a push or a pull, and as a perfect example, the weight of something. You lift something, you feel it in your muscles, right? Weight is a force. So you have push or pull, push or pull your muscles. Second is, of course, something weighs something, so weight. This is the example you should never forget, right? Weight is a force, you're lifting something. Then we also had vector nature of force. So the vector nature of force, and the great example is when you suspend, by the way, the unit is the Newton. Do this again. The unit is the Newton. And then, yeah. So what did we do? We suspended this 10 Newton weight from scales with ropes at an angle, and what we found was the scale would read quite a bit more than 10 newtons. And the reason is that force is a vector, so this red line is what the scale is reading, but since we have colors here, at the same time there's a pull out and a pull up, and this is our 5 newtons. We've got the same thing on the left side, 5 plus 5 is 10. But because force is a vector, the reading is scales as the length of this hypotenuse, so I can take my 5, 10, looks like I got about 13 newtons there because it works geometrically. So we needed what? We needed the geometry of triangles to understand the vector nature of forces. Okay. Generally speaking, everything we've done has needed what we talked about previous to that, prior to that. So that was the vector nature of force, with the arrows. So yeah, you'd want to be able to answer a question like this too. So we've got the vector nature of force. We had also, along with here, we had the law of the balance, we had center of mass, we had Wally Wallington's Stonehenge. So with the vector nature, we were able to understand structures. Post and lintel, arches, domes, bridges, catenaries, that stuff as well. Okay. Good, so we had force, and this was all preliminary to force, work, energy, power. Okay. Force, work, energy, power. So force we already talked about. The Newton work was force times displacement, Newton meter the joule. Now this, of course, energy, the capacity to do work, we needed all that to really get to this point right here. Capacity to do work and power, we have power was work over time. To talk about time, we had the pendulum clock, so I'll just write the pendulum. And the period of the pendulum, the time it takes, and then we had the grandfather clock, which the grandfather clock gave examples for everything here. Okay, that was a crucial formula, the grandfather clock, but I'm going to wait till we have Newton's laws to talk more about the grandfather clock. I'll just write it down here, grandfather clock. Grandfather clock, pendulum time. So at this stage of the discussion, you just want to be able to write down the definition of each of these. So definition plus example. Let me go ahead and write that here. So for all of these, definition and an example, a real life example. Okay. So where are we now? It wasn't enough to know these, although one can do quite a bit with this level of concepts. Okay. After this, we needed the study of motion, because we've built up a complete discussion of energy, and we're going to make it even more complete when we make thermal physics. Okay. We haven't left anything out. So, fifth point here is that we had to study motion, and we focused on free fall, and as a benefit, as an application, we had the satellite orbits. So let me go ahead and write that down and tell you what I want you to be able to deliver. This one is central, still numbering things, yes, 5. So motion, free fall, satellite orbits. This is what I want you guys to be able to discuss. And for that we need the free fall first of all. We had the formula H equals 1/2 G T squared. That was the free fall formula. And here I'm going to specify, when I say G, I mean G on Earth, 9.8 meters per second squared. Okay. And we also had V squared over 2 is equal to G times H. But in particular, we needed this one. Good, so that was the law of free fall. So there's a 1. Then we do the horizontal throw. And here we're just launching, say from height H, and of course, throw a baseball horizontally, it strikes the ground right here. Important, you throw it with twice the initial speed, it goes twice as far. And so from the horizontal throw, we end up with the satellite orbit. So this is one where we, again, have this, just like the shape and size of Earth, this is one of these constructions that you want to understand. Okay. So there's our Earth, there's its radius, we launch horizontally. Oops, let's try that again. I missed the, okay. Launch horizontally, there we go. Okay. So that's a right triangle, labeled L. There's R, and there's that little H right there. But we use this construction to figure out L as a function of how far something falls in 1 second. So this H is 1/2 G T squared, where T is equal to 1 second. Okay, how far something falls in 1 second. We know here, 1 squared, 9.8 over 2 is 4.9 meters. Okay. So we did this construction, and we ended up with L is equal to root 2RH. And a little tricky there, because we did an approximation. Turns out that approximation is exact in the appropriate limit. I'm just going to write approximately. It's close enough. Okay, I believe it's close enough. And when you plug in our Earth radius that I've already erased here, 2h, by the way, that comes just from the Pythagorean theorem here. Let me go ahead and write that out. So here we have r squared plus L squared equals R plus H, the quantity squared, and that's where that L approximately 2RH comes from. Okay. H is a few meters, R is a few million meters. Okay, so that H squared goes away. Good. you end up with 7,900 meters per second. So you want to be able to duplicate this and know the arguments for it, because that's, V equals L over T is equal to 7,900 meters per second. That's the orbital speed. Okay. Now here's the question. So suppose you're able to do all of this, and instead of Earth, I give you G for Mars, or the moon, or some other heavenly body, given, I'll just say G sub moon and R sub moon. Can you do the same thing and find out the speed? It's no longer going to be 7,900 meters per second. It's going to be something else. But the process would be the same, and H, the H that goes into this formula, you'd have to do 1/2 G of the moon times 1 second squared. And instead of the R here, of Earth, you put R of the moon. So I may do that, or the moon or Mars or something else, then you demonstrate this process. But the main thing is to know this whole argument, and the last thing is just the detail. Okay. So that was the free fall and satellite orbits. This number was really important, wasn't it? Because when we talked about the meteor crater, we were able to say, well, it's going at least this fast. And that was when we had learned Newton's law and mass and kinetic energy. Good, so that brings us to Newton's law, mass, and kinetic energy. And let me tell you what the number here is. So 6. Newton's law, okay, mass times acceleration equals force. What we take away from that is that there is such thing as mass, and that weight is, which we already know is a force, is mass times gravity. Okay, so mass, M, meters and what have you. So we'll use capital M right now. The units of mass is the unit of mass is the kilogram, and weight is equal to mass times the acceleration due to gravity. So that was our big takeaway. We needed this. We needed the mass concept. We needed the weight M times G to continue to make progress. Okay. And so here I'll just kind of number these things, what it all meant to us. We were able then to show that kinetic energy, so kinetic energy equals 1/2 mv squared. Okay, so we had that. And then we were able to get the idea of energy conservation. So this is something you have to know. What is energy conservation all about? Energy is neither created nor destroyed, it's changing forms. It's changing form from kinetic to potential. We get the thermal physics, it changes form into heat. So we did all that. Our great example was when the kinetic energy of the asteroid turned into a crater, right? Or was it enough to dig a crater? So we also had the asteroid crater, meteor crater, Arizona meteor crater. Now that's an interesting calculation. That goes pretty far beyond what we're doing on the exam, but it sure is a good example. Okay, Arizona meteor crater. But yeah, energy conservation, if I ask you what energy conservation is, and you say it's about turning the light off when you leave the room, then I know you didn't understand what we're talking about here. So make sure you realize what the energy conservation is all about. And from here, we can consult the clock, see how we're doing with time. Perfect, we've got time. So good, we had that energy conservation. That set us up for the last really big topic, which is hydropower. And here I think I'll review in some detail. I had questions about one of the homework problems or one of the recommended problems on the recent lecture. So are we numbering things? Yeah, so this will be 7. Good, so finally we got to hydropower. This is central to the entire semester. Everything that we've done, right? Structures of dams, for instance, aqueducts, all that great stuff. And what's coming is also playing a role right here. So good, let's have our cartoon up at the water and the dam. And we've got the lower reservoir. We have the penstock. We have the powerhouse down here. Whatever. But yes, we have the height difference between these two water levels. That's why there's energy here, potential energy. Okay. We've got potential energy in the reservoir. It flows out, so potential energy we'll use for W. We now know that it's the weight of the water times its elevation. That's just work, mgh. And we know that as it flows through here, it's being converted to kinetic energy. It's going to spin the turbines here, do all kinds of amazing stuff. Okay. So there's the work. We have the power equals M over T GH. We just set those parentheses like this, and that tells us that's the flow rate of the water. So you want to be able to evaluate this formula. I think I'll set up an example and be pretty explicit about the solution right now. We have power, which is work over time, so that we can solve for the time is the work or the potential energy divided by the power. This is good to tell us how long this reservoir can run before it runs dry. And if you can do these 3 aspects here, you understand hydropower. This is perfect. Okay. And of course we have our water cycle. If we're talking about the big picture, we have the radiant energy of the sun, which is what evaporates the water. There's our radiant energy of the sun. So our thermal physics, we're going to talk a lot about that still. And the rest of the cartoon that I've had here in the past, right? This general cartoon, we're going to draw it more often in the future as well, because it's going to contain everything. Our entire picture of energy will be able to have little aspects of it. Eventually we'll have wind energy too, and then we can draw some wind turbines in here and hook them up to the whole system as well. Okay, so yeah, you want to know that background of the hydropower. The fact that the water cycle is driven by solar energy, the reason this is potential energy is because it's elevated above that lower level. And then if you take a step back and look at it in terms of the water cycle, you can see that the energy that we harness from this is just part of a cycle. If nobody had built the dam, the water cycle would still be there. Okay? The water would just, let's put our mountains up there too, right? There's the mountains. And then it would melt in the spring and flow down. So that cycle exists regardless of whether that energy is being captured in the reservoir and then harnessed. Okay. That's something you want to understand. Good, let's go ahead and actually work one of these problems numerically. So my example, I've got the volume is going to be, say, 100 meters times 200 meters times, and make up a number, 300 meters. Okay. So what's the volume? That's 1 times 2 times 3, so that's 6 times 10 to the 1, 2, 3, 4, 5, 6 cubic meters. So that's the volume. What's the mass? I'll use capital M. The mass of the water, that's my reservoir. The mass of the water is the density times the volume, density of water. So that's 1,000 kilograms per cubic meter times 6 times 10 to the 6 cubic meters. So now my mass is 6 times 10 to the 6, 7, 8, 9. 9 kilograms, right? Kilograms because the meters cubed cancel numerator and denominator. Okay, so I have the volume. I now have the mass. So if I wanted to know the potential energy, I would say I've got the mass, capital M, that's my lowercase m, times G times H. So we would have 6 times 10 to the 9 kilograms. I'm almost tempted to use 10 for G. I will here. 10 meters per second squared, and we have to decide on an H. So those H is just 150 meters. Okay. Times 150 meters. So then we have to multiply that out. So that's 6 times 10 to the 10 times 15. That would be 9 times 10 to the 11. Okay. And what would the units be? Joules. Okay. Okay, I'm thinking I got that right. 6 times 10 to the 10, and then 6 times 1.5 is 9, and then 10 to the 11. So 9 times 10 to the 11. Joules. Yeah, let's keep going. How many kilowatt hours is that? So part 4 from this problem up here, we have 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. That's a conversion factor. We've derived that a couple times. So if I wanted to convert that, I would take my 9 times 10 to the 11 joules, and I'd multiply it by 1 kilowatt hour divided by 3.6 times 10 to the 6 joules. And I'm just gonna wing it here, I'm not gonna write it down. 9 over 3.6, that's just over 2. More than 2, less than 3. And 10 to the 11 divided by 10 to the 6, 10 to the 5. Okay, so you've got several 100,000 kilowatt hours. Good. And if I give a flow rate M over T, you can calculate the power. And if I give, if you have a power and a work, you can divide the work, which is the energy, by the power and get the time, which will be in seconds. Okay. So yeah, that's how we do one of these. And let me stress that if you don't feel so good about all the numerical things, make sure you've mastered the cartoons and labeling them and describing in words what's going on. Should be good. So that's how far we've gotten. We've now gone into thermal physics, but we'll save that for another time. So our exam will have these aspects, right, culminating in hydropower, anywhere from 4 to 7 problems, depending on how we break them up. Okay. So yeah, you want to know all 7 of these topics, and then when I ask you some questions, you just hit the ground running and write as much as you can. Answer all the questions. It'll be great. So let me check the clock one more time here. Yeah, I think that's a pretty thorough review. So if you have any questions, go ahead and let me know in the email. The next lecture, I may mention these things briefly, but we're going to, move on into thermal physics, or continue on in thermal physics. And then Friday, like I said at the top of the hour, we'll go ahead and have our exam. Okay, see you guys next time.